In this section, section 3.1, we're going to talk about extrema on an interval. And extrema is plural. And basically what we're looking for are extreme y values. Now, extreme y values are extremely high y values. That would be the maximum. And extremely low y values within an interval. So let's first look at a closed interval in which the endpoints are included. And let's see if we can determine where you might encounter these absolute high y values. So I'm going to draw a function here. And I'm really only concerned with this function on some interval from a to b. So I won't even draw the rest of the function. We'll just draw a point here and maybe a point here over at b. What is the lowest y value that shows up? Right here. This would be called the absolute minimum. What is the highest y value? Well, that would be up here, and that's located on the top of this hill, and we'll call that the absolute maximum. So absolute max and min are located at the highest y value and the lowest y value. Now, in order to be an absolute max or a min, there must be a point there. It can't be undefined. So I would say this: the absolute min is located at x equals a. The actual minimum value is f of a. So yes, it's a minimum y value, but we want to call out the x that causes it. Right here, x equals c. The absolute maximum is located at x equals c, and the f of c is indeed the maximum value of y, for the interval anyway. We're only really concerned with this particular interval. We don't care what goes on outside. You want the highest y value, you must go to c to get it. You want the lowest y value, you must go to a to get it. What happens in this scenario? This is my function, f of x. And down here, I'm going to make these two line right up. And this will be, again, a closed interval from a to b. And we'll point over here, and we'll say that's the f of a. It's also the f of b. And if you want the lowest y value, I guess you can use either. So the absolute minimum is located at both x equals a and x equals b. And the y value, of course, the minimum y value that you would get on this interval is, it's either the f of a or f of b. It doesn't really matter. Now let's go up here. Maybe this is c, but this is not the f of c up here, because the f of c is undefined, actually. So I don't care what that value is up there, the function won't produce it. This is not a maximum value. So let's say that this lined up with 3 or something like that. Could you say that the absolute highest y value this function produces is 3? And the answer is no, because it doesn't ever produce 3. It produces 2.999 on either side, actually. But will it ever produce 3? No, it won't. When that happens, we actually would say there is no absolute maximum for this problem. And the reason is we just can't put our finger on it. We can't actually specify. We can tell that the curve goes pretty high at x equals 3. But in reality, there's no point right there. So There's no maximum y value. What would the maximum y value be? 2.99999 with 9s going off the page. So where is that? That's hard to pin down. So therefore we just say, I see there is an area that looks pretty high in terms of y, but I can't pin out exactly which y value it is. I can pin down the x value, but I cannot pin down the y value of the max. 3 is really not there. So that is definitely something to watch out for. If it's undefined, you cannot call it a maximum. If you get duplicates, I guess you can do that. You can actually call both of them either the max or the min. What's the formal definition for these extreme values? F of c is an absolute minimum y value as long as the f of c is less than or equal to every other f of x on the interval. That makes sense, right? That says this y is smaller than all the others. Now, if it's smaller, if it's equal, if it happens to be equal, that's okay. That means you have two places where you have that minimum value. But you'll notice it does not allow f of x to be any bigger than that y value. F of c is an absolute maximum y value if that y value, f of c, is bigger or equal, that's okay, to every other y value on the interval. This is the very formal definition of absolute extrema, or extreme values. So where do these values show up? There's only two places where you're going to find them. Take a look at the graph one more time. We'll do this one. Let's do this one. Where's the absolute minimum? Right here. There is no lower y value, and I can put my finger on it. So that is the absolute minimum. Where did it occur? This occurred at an end point. Where's the absolute maximum? Up here, right at the pinnacle. Where did that occur? This occurred on top of a hill. And we have a special name for hills and valleys in curves. The top of this hill we refer to as a relative maximum. And the reason it's relative is because relative to the local area, no matter what's going on to the left or right, you would definitely say if you were hiking on this trail that you were at the top of a hill. Even if this curve later turned around and went right off the page, you would still say, I'm on top of a local maximum, a relative maximum. So, absolute extrema only found at the endpoints or at the relative extrema. And the relative extrema are either going to be hills or valleys. Here's your hill. Here's your valley. And I'm afraid it's going to happen at sharp corners too sometimes. So we got to talk about that. See, a sharp corner has that capacity to provide you with a maximum. That's where you're going to find these things. So let's talk about relative extrema for a moment. Relative. Now I don't really care too much about the entire interval. I care kind of locally, just near the top of a hill, just near the bottom of a valley. If we were hikers, we would say, even though we're at the top of this hill and I see that there are hills taller than this, I can definitely say with confidence, I'm at a local maximum. I've reached a particular peak on this trail. If I'm down in a valley, you very much know you're in a valley. In fact, you can look to both sides and you might not even know what goes on beyond that. And you might not even know that there are valleys deeper than the one you're in. So you very definitely are in a kind of minimum. It might not be the absolute minimum, but relative to the local area, it is definitely a minimum. We call that a relative minimum. How do you find these things? Let's say my curve looked like this, and for now we're going to forget the endpoint, so I'll put some arrows here. Where are the relative maxes and mins? Well, again, on a hiking trail, you would say this is a relative maximum, and this is where it occurred right here. This is x equals C1, let's say. X equals C1 is the site of a relative maximum. I certainly wouldn't call it the absolute max because that looks like the absolute max to me over there. Right here, C2. Now, I'm not really talking about the y values. I'm kind of talking about the x values because the x values are what tell me where to look. X equals C2 is the site of a relative minimum. And finally, right here, that sharp, sharp corner up there, and that's C3. Well, again, if this were a hiking trail, I'd have to say that x equals C3. We'd balance right at the tippy top of this mountain. It's kind of a sharp spike right there. But x equals C3 is still the site of a relative maximum relative to the local area. It kind of looks like the absolute maximum also, but for now we're just talking in relative terms, relative to the local area. How do you find these things? Now, if you didn't have calculus, you would just evaluate the function over and over and watch this function go up, 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 and then watch the function come down, and you'd know that there's one in there. But you might not be able to exactly peg this x value correctly. You'd be sort of hunting back and forth and narrowing it down. Same with this and that one. But calculus will tell us precisely where to look. Because if you look at the slope of the tangent line here, it's 0. If you look at the slope of the tangent line here, it's also 0. If you look at the tangent line here, you'll find it doesn't exist. Curves are considered to be non-differentiable at sharp corners. So actually, f prime is undefined. But you'll notice, just so we make sure that we check it, that the function itself is defined. So we got to check that to make sure that it is. Okay. So look at what we found. Calculus is going to help us find these x values that get us these relative maxes and mins, these hills, valleys, and also these sharp corners. But we're going to have to look for them in a couple of different ways. So to find C1, C2, and C3, which, by the way, we refer to as critical numbers. They sound pretty important, and they are. To find your critical numbers are the sites of relative maxes and mins. And to find these critical numbers, you want to do two things. The first thing you want to do is discover where your derivative is 0. That's the first thing you should do. The second thing you should do, and that will cover hills and valleys. Now, as a side effect, and it's unavoidable, it will also cover a flat spot too. Now, we don't really want the flat spot, but we're going to get it anyway, and we'll have to sort those out. So what do you find? You'll find relative maxes here on top of these hills. You'll find relative minimums on the bottom of these valleys, and you will also find flat spots. All right. Number two, the second thing you want to know is where is f prime undefined? Now be careful with this one because there's two different versions of f prime being undefined. One version of f prime undefined would be something like this. I'll remind you that if a function is undefined, the derivative will also be undefined. So we will pick these up, and these aren't really relative maxes or mins. I mean, they go to infinity. So that's not really what we're looking for. It has to be defined. So make sure that f of x is defined. In other words, there's a point there. Now, how do you get the derivative to be undefined and the function defined? Those are sharp corners, okay? And you'll pick up these two. So this is also a relative maximum. This is also a relative minimum. It's just a very spiky version of those two quantities. Okay. So I think the best thing to do here to find these relative maxes and mins is to do a couple of examples here. And then we'll graph what we find out. So let's do this. Let's find the relative maxes and mins. Oh, I guess unfortunately we're going to pick up flat spots when we do this too. Really, I should say, let's find the critical numbers. When you find the critical numbers, you're going to be finding all of this stuff. So flat spots come as a side effect. It's unavoidable when you set f prime to 0. So let's do it for this function. Now, if you were in pre-calculus or algebra and trig, most you could do with this, I suppose, is you could graph it, you could find the x-intercepts, you could find the y-intercepts. This power here and this coefficient give you ideas about end behavior. This number tells you how many zeros or x-intercepts you could have, and then you could graph it. But the problem is you're not really equipped to find those hills and valleys, which are very important locations on this curve. But we are if we go for our critical numbers. So find the critical numbers. That would be when f prime is equal to 0, and also when f prime is undefined. And you know what? On that one, we have to also back it up, and we want f of x to be defined when we do that one. So that goes together. Let's do f prime over here. F prime of x, derivative would be 12x cubed minus 12x squared. And let's set it to 0. Factor out the 12x squared, leaving me with an x, leaving me with a minus 1. Divide by 12. We don't need that 12. That is not a critical number, by the way. Set each factor to 0, and there they are, guys. The critical numbers, 0 and 1. Now, what exactly shows up at 0 and 1? I don't know yet. And we need to investigate that further. For now, find the critical numbers. Now, you know what's going to be there. We set f prime to 0, and that particular kind of critical number gives us three different things. A relative min, which is a valley, a relative max, which is a hill, or a flat spot. I know that at 0 and 1, I've got one of those three things. So what I'd like to do next is I'd like to graph that function, and let's see if we can find that. So I'm going to bring up a nice website here that has a graphing calculator on it. It's called Desmos. So you can use this as well, or use your graphing calculator. So we're going to put that function in. F of x or y is equal to the function 3x raised to the fourth power minus 4x cubed. And let's come on over here and take a peek at what happened. There's absolutely no question that we found our critical numbers. Remember what they were, guys. 0 and 1. Well, right here at 0, you see we found a flat spot. We're not big fans of flat spots. We really want relative maxes or mins. The problem is we pick them up anyway. So that's what we got. Later on, we're going to call this a point of inflection. Okay? That's for later. For now, we can still call it a flat spot. Over here, look at it. X equals 1. Bingo, we found ourselves a relative minimum. In fact, based on the picture, I think it's pretty clear that that is an absolute minimum. That is the very lowest y value. But it did call out the relative minimum, meaning it is a valley. So it worked. F prime equals 0 gave us what we were looking for. We found hills, valleys, and flat spots. What about the second thing that we might need to do on this? Because there really are two different things that you need to do to find critical numbers. Find critical numbers, you set f prime to 0, it did that. How about setting f prime to undefined? We'll take a look at f prime here. Will it ever be undefined? The answer is no. So I guess we don't need to do that particular step. F prime will never be undefined. How would f prime become undefined? Let's talk about that. So I'm going to find a good example here where f prime does become undefined, and then you'll see what the results of that will be. So let's take a look at this function. Just as before, I'd like you to find the critical numbers. And let's talk about how we do that. Now, you got to do two things. Number one, you got to set f prime equal to 0. Number two, you got to set f prime to undefined. And also, while you're doing that, be careful. Make sure that f of x is defined. Otherwise, you have yourself, most likely, an asymptote. So we don't want those right now. All right, I think what we should do is find f prime. First of all, f prime of x is equal to the derivative of 2x is 2 minus 3 times. The 2/3 drops down like this. Deduct 1 from the exponent. That would be x to the negative 1/3. F prime is therefore 2 minus 2, and the x to the negative 1/3 shows up really down here as x to the 1/3. All right? Let's keep going. My recommendation when you end up with derivatives that are fractions, get it joined together and make it one fraction. That's really going to help when we do critical numbers. So that's really what we should do next. Let's get this together and make it one fraction. Now, how do we make it one fraction? You need the lowest common denominator, which would be x to the 1/3. Let's put one here and one here. And in the end, we get 2x to the 1/3 minus the number 2 all over x to the 1/3. Now, I think we know what x to the 1/3 is. It's a cube root, so let's write it as a cube root. I realize this is not in simplest radical form, but that's okay. We can use it as it's written right now because we're going to do two things. Number one, we're going to set this fraction equal to 0. What fractions are worth 0? All of these. So to set a fraction to 0, all you really have to do is set the numerator to 0, right? So we're going to take 2 cube root of x minus 2 and find out when that's 0. I think we can do that pretty effectively here. 2 cube root of x is 2, divided by 2. I'll bring it over here. The cube root of x is 1, cube both sides. and I found one. Now, you set the first derivative to 0 by setting the fraction equal to 0. And when you set the derivative equal to 0, what do you expect to find here at x equals 1? A hill, a valley, or a flat spot. It's got to be one of those three items. Okay. Number 2. Let's take a look at number 2 up here. Number 2, we're finding critical numbers. Don't forget, I want to know when f prime is undefined. That would be number 2. So number 2, when is f prime undefined? But f of x is defined. How do we do that? Well, I know how to make f of x undefined, f prime, I'm sorry. Which of these fractions is undefined? All of them. So divide by 0, no matter what, even this one is undefined. Let's do it then. Let's find out when the denominator function, cube root of x, is equal to 0. And that will cause that derivative to be undefined. Cube both sides, and you realize that it's x equals 0. Now be careful. Is x equals 0 a critical number or not? The only way I'm really going to know this is if I try x equals 0 and make sure the original function is defined. If the original function is undefined, chances are that x equals 0 is a vertical asymptote, not a critical number. So let's try it. F of x, the original function was 2x minus 2x to the 2/3. Let's try x equals 0 to make sure it's defined. And it certainly is defined. It happens to be 0, and that's fine. So I'll check that one off. It's a critical number. Now, when you find a critical number in which the derivative is undefined, what does a curve look like when the derivative is undefined, but the y value is defined? That would be a sharp corner, and it's either one of these. So we definitely have a sharp corner at x equals 0. Some kind of sharp edge. The derivative does not exist at sharp corners, nor does it exist where the function itself is undefined. But the function is defined, so that must be a sharp corner. So let's take this function here, and let's see if we got what we expected to get. And that is a sharp corner at x equals 0 and a hill, valley, or flat spot at x equals 1. So let's plug that function in to our graphing calculator. So the function is 2x minus 2x raised to the 2/3. Now let's see if we got that right. Nope, I didn't get it right. This is 3. There it is. I knew something was wrong because the critical number didn't line up. Now let's take a look here, guys. As promised, isn't that amazing? Right there at 0, sharp, sharp corner. Also, as promised, right here at x equals 1, we got ourselves a valley. I'll zoom out so you can see that valley a little better. So we are getting exactly what we're looking for, and we're getting it by finding the critical numbers. Now I'm going to leave you with one last concept, and that is to tie everything together and find absolute maximum values and absolute minimum values on a closed interval. So I'm going to provide you with a closed interval, and I'm going to say, tell me, where would you find the absolute highest y value? Where would you find the absolute lowest y value? And tell me where. Give me the x value. And, of course, give me the y value as well. So to do that, we need to revisit this concept of absolute max and min. Absolute max and min. Where would you find these things on a closed interval where we tie it up between A and B? Well, let's take a look. This particular example, the highest y value occurs right here at the top of the hill. I'd have to call that the absolute max. That was the top of a hill. The lowest y value occurs at the bottom of this particular valley, absolute minimum. And the endpoints are not very important, I guess, in terms of absolute max and min. That's not an absolute max or a min, and neither is that. So certainly one site of potential absolute max or min would be at critical numbers, which also means at relative maxes or mins, relative to the local area, which are always hills or valleys or spikes. How about another example? A and B. There's no question that there are many hills and valleys. Here's a valley, here's a hill, here's a valley, here's a hill. There might even be, well, no, that more looks like a flat spot in there, so I'm not going to call that a hill or a valley. But I got to tell you, I'm going to push this up just a little higher so it doesn't interfere with that one. I'm coming across, and I'm calling this one the absolute maximum. I'm coming down here, and I'm calling this one the absolute minimum. So where else would you find absolute mins or maxes? You could find them at the endpoints. So the bottom line with finding an absolute max or min on an interval is you will either find them at critical numbers or the endpoints, nowhere else. So let's do a problem. Let's do a problem here. What I'd like to do is find the absolute max and min on a closed interval. And I'm going to pick a problem from the book. Let's pick, how about problem, let's start with problem 21. This is from the homework. Problem 21 says f of x is equal to x cubed minus 3/2 x squared. And the interval will be, the closed interval will be from -1 to 2. Find the absolute extrema. That's plural for extreme y values. So I mean both the maxes and the mins. First thing is, let's get our critical numbers out of the way first. Remember, critical numbers are discovered by setting f prime to 0 or undefined. But also, if you do the undefined one, make sure that f of x is defined. Well, I don't think we need to worry about undefined on this problem. This is 3x squared minus 3/2, and the 2 drops down, and I get a 2x. And we want that all to be equal to 0. We want to do this one. 3x squared minus 3x equals 0. So that's going to be a 3 factored out. And, oh, an x factored out as well, isn't it? And that leaves me with x minus 1. Let's just make sure we got that right. 3x squared, 2x, 2's cancel. The 3 comes out and the x comes out. Now, people are telling me that 3 is a critical number. That is not true. In fact, throw it away. That has nothing to do with my critical numbers. These are my critical numbers. Now, we know what's there, right? These particular critical numbers have either hills, valleys, or flat spots. Now, I know a flat spot is not going to help me find an absolute max or min, but I'm not sure which one I have. It's one of these 3 items, so possibly one of these, meaning it could possibly be the absolute maximum. How do we do this? A simple XY table will save the day on this problem. Now, what I need over here, I need the critical numbers, because critical numbers could possibly be the site of an absolute max or min. What do I need over here? I need the endpoints of my interval, because the endpoints are also potential sites of maxes and mins. And we have all of that information. Here are my critical numbers. You're going to have to go work for those. My endpoints are right there. What about down here? Well, down there you're going to have to do some calculations. So I'm going to get my calculator ready here. And if you have a graphing calculator, it actually goes even faster. But let's start off with 0. 0 cubed minus 3/2 0 squared. Don't think we need much for that. 0. Let's put the 1 in. That's going to be 1 cubed minus 3/2 times 1. That's minus 1/2. Let's put the minus 1 in. Minus 1 cubed is negative 1, correct? Minus 3/2 times 1. So negative 1, which is negative 2/2, minus 3/2, is negative 5/2, or minus 2.5. And let's finish with this 2 here. 2 goes in, you get 2 cubed is 8. 2 goes in, you get 2 squared is 4 times 3. That's 12 over 2, which is 6. So what are we getting here? 2. Let's double check that. 2 cubed is 8. Minus 6 is 2. So now what? The only places you will find absolute maxes, absolute mins, are at the critical numbers and the endpoints, and you don't have to look anywhere else. Well, luckily for us, we have all that information. There are the critical numbers. There are the endpoints. So how do you finish this, guys? You just circle the absolute smallest y value and call it for what it is. You just circle the absolute largest y value and call it for what it is. It's the absolute maximum. So there's my absolute min, there's my absolute maximum, and sure, there's stuff going on here and here, but apparently these are not big or small enough to be considered absolute maxes or mins. Now, if you really want to see what's going on here, we could again go to our graphing computer here, our graphing calculator, and we'll do that. And I'll plug that function in. So our function here is x cubed minus 3/2, and it's x squared. Let's see what that looks like. So we take a look. Now the interval, remember, it's an interval between -1 and 2 only. So I'm going to really tighten up my x-axis. I'm going to go from -1 and I'm going to go to 2, and that's it. So let's put this away. So this is all you get, guys. This is all we get, from -1 all the way to +2. Well, sure enough, as promised, -1 does produce the lowest y value, which is a -2.5, and +2 does produce the highest y value, which is up there. In fact, you can't really see it, but there it is. It's up there at 2. So were there things going on at 0 and 1? There certainly were things going on at 0 and 1. We got a hill here and a valley here, but those hills and valleys were not big enough, really, to affect my absolute max or min. So I encourage you to do this. Go to the homework. Find those critical numbers. And yes, some of them you're going to have to find critical numbers by setting f prime undefined. Now, how do you do that? By setting the denominator to 0. And then find those x values. Those are special, so you want to back them up. Make sure the x values go back into the function and make the function defined. And now you very well know you have a sharp corner there. But when you're doing this problem, you need the table. So I want you to put a table out, put your critical numbers across the top, put your endpoints across the top, and down below are just y values. Just compute them, and finally, circle the big Y, circle the small y, and those are what we're looking for. So that's it for today on Extrema on an interval. Thanks very much.